meaning we need to set it up in VHDL at some point. Okay, fair enough. We'll do some of that. Yeah, the VHDL, setting it up to 16L8 in VHDL, that's going to be like a case statement, I suspect, probably. Case is going to do the job for you there. Have you guys had a little bit of VHDL or Verilog in the past up until now? Verilog? Okay, Timur says we had Verilog. 212? Okay. Okay, good. Good, good, good. So you guys are already familiar with the case statement then, theoretically. 16550 are decoded in the high bank at odd port address from FFE to FFE1. We would just interact with D8 through 15 while addressing even or both use the high bank and odd addresses. Good question. Good question. I was trying to think about that one myself. You got that. Basically, address 0 is the BLE signal, right? So 212 did not cover Verilog for you, Deneen? There is a case statement in Verilog and VHDL. That's a pun on several levels, Patrick. That's pretty good. He says 212 threw us under a Verilog bus. You realize that the additional level of bus and so forth in there. I remember writing a test bench. There was an add word. Okay, didn't cover Verilog either. All right, let's tell you what. As long as we're flying by the seat of our pants here, let's try one more thing while we're class is firing up here. Let me get this going. What do we got going here? I remember debugging the clock for 3 hours. Okay, that's possible. All right. Now, I'm much more familiar with VHDL than Verilog, but it doesn't mean I don't know it. I know it's a case statement in VHDL. I think it's a case. There's a case statement in Verilog as well. Yeah, there it is, case statement. All right, we can talk over this a little bit. I can fly by the seat of my pants. Yeah, here we are. Thank you. It was roast beef. Okay, good enough. Jackie, sorry, I'll do that later. Thanks. Okay. So here's a case statement in Verilog. Thank you. Let's get that up here. Yeah, that'll work. Let's see, case. Okay. All right. All right. So Verilog, let's get up over here. Verilog has this concept of a case statement. I'm going to kind of get you guys in on this, especially. So if you're doing like a, what we're doing here with this guy, but this is test code only. Okay, I believe you. All right. So this is the basic fundamental construct for a case statement in Verilog. What you're doing is you tell Verilog what you're testing with. Okay. So in this case, he's got 3 different inputs. He's not using all 3 of them. There's up to 8 different possibilities here. All right. And what he's doing is he's saying your output's going to get loaded with a particular value at that point. So how do you do it backwards as a decode rather than this is an encode. Let me try another one here. Let's try a little bit more. Syntax, 5 different programming languages in one. Yeah, not exactly. I just grabbed an example for log case statement. Okay, so there's exactly how the case statement is done. An example. Out equals A, out equals B, out equals C. You might want to do this a little bit different, though. You might want to. That's how you do a mux. You guys are looking for a demux. All right, let's try one other thing here. Let's try this a little bit more. A little more case statement demux. Yeah, that'll do it. Not all that elegant, but there we are. Oh, okay. Yeah, that would do it. I think I'd probably be a little bit always at D or cell. I think I would think what you can do is I have to double check it. That's one. You want to make sure that if it's not going to be held low, you want it to be held at a 1. And what you do is in the begin statement here, you kind of have a default. And so you'd say Z0 equals 1, Z1 equals 1, Z2 equals 1. You'd put a set of equations. So let's do this. Let's do this. Oh, that's not what I want. Sorry. There it is. All right. Is this an image or can I grab this guy? Like an image. All right. So let's do it from here. Oh, is at E or SEL. Now again, I'm not, Verilog is not my strong suit. Begin. I'm going to say Z of 0. Let me do this here while you guys are watching. You have to hear me talking. I'm going to change this a little bit. I'm going to say Z of 0 equals 1 tick B 1. I think that's all you need. Semicolon. Right. Yep. I'm going to say Z of 1 bracket equals 1 tick B1 semicolon. I'm going to repeat this a few more times. Notepad. All right. Becomes 2. That becomes 3. That becomes 4. That's 5. That's 6. Can anybody see this okay? The text big enough? Larger necessarily very easily. Okay. All right. Good enough. So then you're going to say case. Okay. Yeah, you can record the session. That's fine if you want. Case parents SEL, close parents. And then you're going to say what we've got there. 3 tick B 0, colon Z of 0 equals 1 tick B0 tick B0 semicolon. And then you're going to repeat this. All right. N becomes 2, this becomes 3, and this becomes 1, and this becomes 1, and then now, as long as we're sharing the wealth, all right, so this becomes a 1 and 1, and this becomes 4, 5, 6, and 7, and I think we're pretty close. So then we go end case, and then we go down here and we go end. I'm not showing the whole code, okay? I'm just starting from this always. So you still need the same stuff up above. You forgot the last one? Oh, you're right. Thank you. All right. So up above here, we're going to have module, emux, e comma, sel, comma, z, where z is the output, of course. And then we're going to tell them input d semicolon, input 2:0. Actually, we don't have d. We don't even need an input d at this point. So we're not even looking at d at this stage because we want it to decode a solid value. So what I'm going to do here is we're going to even get rid of that line. Confusion, theoretically. 20 square bracket, CL semicolon, output square bracket 7:0 square bracket z semicolon. I'm going to say reg 7:0 square bracket z semicolon. I think that should do the same demuxing function that the 16L8 does. So what you could even probably do if you want to get a little more fancy with this, underscore 16L8. I believe that will do it. So what happens is that you set up your outputs to all be ones, and then the case select comes into play, okay? And then whichever one decodes, it sets that output to 0, but leaves the others as 1s. Okay, so does that make sense to everybody on how that works? Okay. That making some sense on how to do the 16L8 decode in your Verilog? I think that might be helpful. I'll save this file and I'll put it up somewhere for you guys if you like. I'll put it up on the blackboard. Okay. All right. You want to put that back for another minute or two, or you guys got it? Anybody need any? Let's put it this way: no news is good news. If you don't say keep it up, I'm going to put it aside. All right, I'll put it aside. All right. And we'll kind of pull this down here too. All right. So, any other questions that people have about how to do their code going forward? Because at this point, I want to launch into this example here and kind of work on this with you guys. Those of you who want to stick around and see how to do it. Okay. All right. Seeing no feedback, I'm going to barrel on ahead then with this. I'm going to leave it in the PowerPoint presentation thing here. Because I'm probably going to be moving stuff in and out on top of it, and I don't need to be forwarding too many things. So, all right. So the idea is we've got an address bus that's only 18 bits wide, not the full 20 bits. We've got a data bus 16 bits wide in the data bus. We've got system controls. We've got a byte high enable, a byte low enable. Okay, and 80 is going to be doing the byte low enable signals for us. Main concern we're going to have that is doing our write. Okay. There's a write active low, a read active low, and we're going to choose between mem or IO. Okay. As far as I can tell, would you consider the system has line the control bus? Not sure I answered that question here, sorry. The BHWR and RD. So BHE is not high enable. Would I consider all of those control bus? Yes. Very good question. Very good question. All of those are the control signals. There's the address bus, which is 18 bits. The data bus, which is 16 bits, and the control bus, which is made up of all these different signals. That's a very good question. Very good point. Very good point. All right. So what we'll do now is when I have 4 banks of EEPROM memory. Okay. They use 4K by 8 chips. And I had one of the old examples we used back a while ago. I want to bring that up and kind of use that as a template here. So let's bring this guy back up. Okay. And if I remember correctly, we got this sort of thing going on here too. So this is pretty close to actually what we're looking for our RAM memory interface. Okay. And it should be like what you guys are using for some of your design. Okay. The thing is that we don't have 18 memory bits here. So 19 and 18 go away. All right. So this piece here goes away. Block it out. And there might be a way to kind of do this a little bit here. We're drawing as we're going. So let's try and do this here in real time. So let's I'm gonna get this here. A little bit. All right. So we decided that these top things go away. Hopefully I won't have to go back and put them back. But these go away. And that means this whole thing here goes away, I suppose. Okay. And all the stuff related to him. That goes away. Is this helpful? And we'll figure out these here in a minute. All right. And so I know the green text has gone away and the red lines have gone away. This is regarding decoding. Yes, I'm working on the decoding thing now. I did the 16L8 in Verilog type sort of situation. And let's see. So the address, we're going to have to capture the address values in an address buffer. And here's the next question. We got to go back. We got to go back and look at what we had on the previous slide. So give me a second here. Nope, not that one. Not that one. I want this one. Here we go. All right. So there are 4 banks of 8K using 4K by 8 chips. So let's settle into this for just a second here. Right now I'm doing the EEPROM piece. 4K means how many address bits do I need to get the 4K by 4K addresses? Supposed to have 4 chips for decoding. Yes. But let's talk about address bits first. I'm going to start from the bottom and work my way up here a little bit. So 4K, the number is the address range I need. I got 4K by 8 chips. How many address bits do I have on a 4K by 8 chip? We're going to work on this one for a while. How many address bits do I have? Do I need for a 4K chip? A K is going to chew up how many bits? Okay, 12. That's right. A K is going to chew up 10 bits, and then to get to 2K would be 11 bits. To double that in terms of a K, I got to get to 4 bits. 2 to the 12. Very good. So 2 to the 12 is 4K. That means I have 12 address bits I need to have for that thing. So let's go back to our little example we're whittling on here. Get that brought back forward. Okay, so I'm going to have, we said 12 address bits, right? Okay. So what's going to happen here is I'm not going to have a range from A0 to A14. That's going to be 32K chips, right? So for this example, that 14 is going to change into a 12. So these guys actually go away here now in this example. And we're probably going to tie them to ground. Let's do that. We've got them there. So let's grab these here and tie that to ground. Actually, you know what? Let's see, I got the 1G as well. So we'll do it this way. We'll do exactly the same way they've got it there. So this is the same sort of thing we're going to need here. And I'm going to put it there. All right. So this, we're only going to need 12 bits to do that. We're going to have to use the 2 more bits to select it, right? And so let's not lose too much of that. All right, so 12 is what goes in here now. I'm just going to kind of grab that and put it over there. I need a number 2. Come on, grab them. You change your size, I want you to just grab them. Hang on, sorry about this. Can't we just place a no connect flag? Really, you're going to want it grounded. You are going to want it grounded. You're going to want it going somewhere solid. Technically, it could be a no connect. Oh, you're right. That's a good question. Very good question. All right, hang on a minute here. All right. When you place it, when you put it down there, it's going to have to put it there. Guys. Trying to get a 2 over here. Oh, come on. Wait a minute. I remember how this works. Hang on. Here we go. This will get me there. All right, so that becomes 12 instead of 14. And ditto on the one down below. Okay. And just so we don't have our 2 sitting there anymore, let's fix that. Hello. Is that power using in Paint? Okay, so that now has our 12 bits there, 12 bits there. We got too many of these guys, right? And we really only need one group of 4. So these bottom 4 are going to go away. 1, 2, 3, 4, at least 4 up on top. And this bottom 4 are going to go, piece is going to go away here. Quite that far just yet. This seems like the best way to do this as far as I can tell at this stage of the game. One more up. Done some fair amount of editing on these guys over the time. So, oh, come on. Just got through bragging on myself and then I fell down. Nope. Come on. Sorry. There we go. So we're not going to use these other outputs here at the moment, including this one. Go back up. So you were talking about the NC flags. You're going to put 4 NC flags on these outputs here. Okay? And I'm not even going to need this bottom bank here because, well, I just need to have the output data bus. Can we place a no connect flag and input? No, actually no connect flags are going to be more on the outputs than the inputs. So Sure. TY, I'm sorry, guys. I'm not that good at. What's TY mean again? Thank you. Thank you. Okay. I remember that. Hey, I'm getting smarter in my old age. Yes, sir. All right. So at this point, we're going to have the address bus continuing across here. He doesn't need to go down to the other stuff, which means all this stuff continues across here like this. And then this goes away like that. I'm going to have to get the command control words in here shortly. And I'm going to take this data bus. And how am I going to do this? Let's do this. Let's grab you. And I'm going to rotate you right. Wrong way. Flip horizontal. Put you over here. You guys can tell I've done this a few times, I guess, right? And it's got to be IO, right? So it does. So I'm going to do the data bus. Move it up here. Like so. And I'm going to get rid of all this. And all of this. And all of this. All right, so we're getting there. All right, so does that make some sense now? We've got this is just doing the memory side part of things. And it's doing it on the fly. I would be drawing it on the board if I wasn't. This, let's get over here. These numbers here and stuff don't apply anymore because they're 4K. They're 2K by 8. That's exactly that. He's got 4. I don't know what that was. Why that would be 814? I don't know. Let's see. So is this considered banked high and low? That's an interesting point. Good point. Actually, I need the low half of the bank, don't I? All right, so maybe I'll put it back. Was it the other part of the bus? The bus. You're right. I do need the 2 halves of the bank. Good catch. Thank you. So we're going to do that. But I don't need the bottom 4 here for sure. 2, 3, 4. Good catch. Thanks. 1, 2, 3, 4. Okay. Again, we can do the same thing here. We can get rid of at least the bottom of you guys. And go over here and finish up this. And so again, on the unused outputs here, 4, 5, 6, and 7, you're going to have the no connect flags go there. All right. So then back to my previous question, if you have 4 chips of memory, but you also need it banked, does that mean you need double the memory for the high and low data buses? So what's going to happen is the see, can you guys? Yeah, you guys can see me here. All right. So the top 4 things here, clean that up just a titch. These guys here, that's your top or bottom 8 bits. We'll figure that out in a minute of the 16-bit bus, right? So these are 8 bits for your data, and then here's the other 8 bits for your data. You have a 16-bit data bus altogether, right? And we're just going to assume that they magically get mushed in together, so that like this is probably going to be D0 through 7. This is going to be D8 through 15 for this part here. Okay. And yeah, you may have the directional and the buffer, I suppose, the 74 LS 245. I can't remember if you can have one of those guys or not. Okay. And now your 16L8. Oh, did I get rid of the address there too? I did, didn't I? Okay, I got to put the address back first as well. So let's go back a ways. Hang on, I got to put the address thing back. Sorry. We want the address bus to go back. Okay, Control Y. All right, so I got to put that address bus back. Sorry. Just realized I didn't have the address bus going where I wanted it to go. All right. And so now we decided we can get rid of these bottom 4 though. Okay, I think that's it. And these bottom 4. And then again, we can do this. Come on. Hi. Anybody that said professors don't make mistakes hasn't watched me very long. That's assuming I'm a professor, I guess. There we go. Okay. Okay, I think that's got a little bit more accurate now. So the big thing is that, and I may have to kind of wave hands a little bit here as I go on, but okay. So you have no connect flags on 4, 5, and 6 here, right? So the address bus, you're going to have 0 through 12. You're going to ground these top 2. It's not going to matter anyway. But your address busing is coming through here, and your address bus is going to pick up 0 through 12 and come out here and go to the 2 groups of the upper data bank and the lower data bank. So the BH, depending on which one's which, let's make some note here. Let's take a 15. Put that here. Oh, it's up there. Okay, fine. Nope. All right, hang on. Okay. Here we go. So 15 goes there. Clean up the bottom part of it just a titch. All right, so there's 15. We needed them decoded at what address? At this point, okay, that's a good question. That's a good point. Hang on a second here. We'll get the top part decoded here because we still got the top bits to play with. Need them decoded at address. This is a lot tougher to do without a board, you realize. Okay. They need to be decoded at starting at address 1000 hex, or one with 4 zeros after it hex. We'll get to that in just a second. Okay? Good question. All right. We'll get to that in just a second. It's got to be absolutely that address. Is this helping a little bit for some of you guys? Hopefully I'm not boring you guys to tears and or getting you completely lost. All right. So this has got to be 7 through 15, 8 through 15. I need an 8. All right. Well, bear with me a minute here, Andrew. I think we'll try and I'm trying to get this drawn as I go. Control V. I'm not through yet, so hopefully I haven't left you all the way just yet. But I'm kind of trying to draw an illustration without a whiteboard in front of me, and this is easier than trying to do the hand stuff. All right. So this is going to be data bits 8, and I got to find a dash somewhere, through 15. All right. And so we'll need a dash somewhere. Yeah, it'll work. I'll steal it there. Give me a move here. Don't give me a stretch. Ah. Sorry. All right, let's do it this way. That'll do. Okay. All right. So this is data bus. This is the data range. All right. So zooming in here. So we've got addresses 0 through 12. We're modifying that original diagram that we had. Okay. All right. And we're going to put the data bus, data bits, the address range is going to go to the same to both of these guys. Okay. All right. But when we do data bits, the data bus is going to be able to go in or come out. we're going to peel off the top 8 data bits. That's going to be data bits 8 through 15 to go to this particular chunk of RAM. How many RAMs did he say we have? 4? 1K? Let me go back. I'm sorry. I may be losing this. 4K by 8 chips. Using 4K by 8 chips. Okay. 4 banks of 8K using 4K by 8 chips. All right. So 4K means we got the 4K part. We got the 8 by 8 chips. He said 4 banks. Okay. By banks, he means 4 pairs in this particular case. All right. So what we've got here is here's our 2 banks. Here's the bank of the lower data bits. Here's the bank of the upper data bits. And this one now and then is going to be 7 down to 0. Hang on. This is going to be 7. All right. So 7 goes here. And I'm going to grab my 0. Lots of zeros to choose from, I'm sure. And I'm going to grab one more here. Okay, so that might help a little bit. So we've got the fundamental chip. 1 bank equals 2 chips. We have 4 banks here. Yeah, or you could think of there's an upper bank and a lower bank, in which case, either way you want to think about it works. Okay. So, but in order to make up the full data width, I'm going to need at least 2 chips to do that. All right. Because each chip has only 8 bits of data wide. So I'm going to have my data bus here is going to be picking up the top 16 bits, and the data bus up here is going to be, so here's 8 bits here. 8 data bits are going to go to here, and another 8 data bits are going to go to here. You combine those 2 groups of 8 data bits all together, you've got 16 altogether going in and out of this 74 LS 245 buffer. And that was what he actually originally had for the design, except that he had a bigger chip to work with. He had a bigger memory chip to work with in the original one. Ours is only going to be, actually, that's not even the right number there. Huh, you guys didn't catch me on this one. We need 12 address bits, right, to do 4K? Okay, which means this 12 is not correct. What's the number I need there instead of a 12? Is anybody going to catch me on this one and fix me on it while I do the editing? 11, that's right. Melissa, you get the gold star on that one. Very good. So this actually needs to be an A11, which is even easier to make in terms of this drawing. Switch down. Hang on. Try that again. It'll look a little bit better too by the time we get done. All right, so there's an A11 there. And I need one here too. All right, so A11 means I actually have 12 address bits. Everybody with Melissa on that one? As long as I'm down here, should I clean some of this up too? Make it a little less confusing. I'm not sure it's going to per se, but we'll try. And then I can do this here. At least clean out some of this a little bit. And a little bit more cleanup here. Okay. Yeah, those were getting elegant. All right. So going back out here now. All right. So now I've got I got 8 chips all together. Isn't that what the requirement was? 8 chips all together? Right? I've got 4 banks of 8K using 4K by 8 chips. Well, it doesn't say how many chips I have exactly, but 4 banks, I'm going to need 8 chips all together. All right. 4 of the chips are going to be holding the lower part of the memory, and 4 of them are going to be holding the upper part of the memory. 4 banks of 2 chips each. That's right. And or if you think of the 2 chips are what you need to make up your 16 wide data bus, because one's going to have 4 data bits, the other's going to have 4 data bits. All right. So that's what we got there. The addressing, and so actually this isn't even right for the addressing up here for the buffer either, right? Because I got one too many address bits there too as well. You guys got to catch me on these things here. Let's fix that here a little bit. That'll be as good as we can do. All right, part of the reason to do this exercise too, by the way, is for those of you who are watching at home, bump this over one more. It's just a titch. All right, that may be as good as it's going to get. There we go. All right, so now I've got 12 address bits that are going to, the bottom 12 address bits are going to be going in here. And to be honest with you, A0 is actually your bank select. So maybe I'm going to put that back. Hang on a second here. Put that back for just a minute, because I do need A12. The thing is, I'm going to use A0 as my upper and lower half of the bank select. And I'm not sure how I'm going to do that exactly, but at the moment, I'm probably got this not exactly correct. So let's do this. Let's move these guys up a notch. I think A1 actually wants to go into the top here. I think A8 wants to come down here. I'm going to apologize for the mess it's going to be. A8 wants to go down there. Let's do this different here. Grab the 8. Maybe if we just grab it instead of stretching it. Let's try it again. Have A down here. You can get there. Come on. All right, another A. What I need is an 8. Okay, so wait for the project. 32K by 8, which means 32K addresses. Okay, so chips are 32 by 8. Good question. Let's deal with that a little bit as I'm going on the fly here. So if they're 32K, chips are 32K by 8, how many address bits are they going to have to cover 32K? Who's going to try and get another gold star here for me? 32K, how many address bits do I need? 15. Melissa got there first, but Colby's right behind. 15 is the correct answer. So in that case, your address range is going to go. Now, here's the other thing, though. You guys were noticing that we're not going to use that bottom address bit. What I am going to do here is now, let's do it this way. I got to think about making this work as I go on the fly, but this is going to move up to there. And now this is going to come up here. Okay, I think that's the way I want it to be. So what's going to happen is we're going to need 11 or 12 address bits to access the RAM. Now, what's going to happen is, remember that we talked about how you take that bottom address bit and you just kind of sort of throw it away? So What you may or may not need the buffers. I don't know. It's up to you guys. You have to decide how that works. But based on the requirements for your particular design. So I got to have A12 down to A1. Now that is 12 address bits. That's going to map into A0 to A11 on my banks. Okay, all right. A0 is going to be choosing between which of the two banks we have going, whether we've got the lower bus enabled or not. Okay, and then the higher bit is going to choose on the other one. So we make it a little exotic with that yet, but and we got to look at these 74 LS38s here. Okay, and probably what we're going to do here now is I'm going to use the enables on these two guys here as being my what I want them to be. So I'm going to take this guy here. All right, well, let's see. We're going to have to, A, B, and C are going to choose. I'm not going to need C because C is going to only just select the bottom pieces anyway. So C, I'm going to tie to 0. A and B. Yeah, I'm going to tie C to ground. So we're going to get C tied to ground here. And actually, I want C tied to ground exclusively. So give me one more second. I want this to come in here. And I want this to go away. Come on, select it. And I want this to go away. Get rid of that too while I'm at it. Now I got C going where I want them to go. So I'm going to tie C to ground here. I may need to come back and redraw those guys. And I'm going to try C to ground here. No, not that C. What do we got going? 2K by 4. Hang on a second. Oh, look at that. Okay. The side ties C to ground here. And I only want A and B. And so this is going to go from 3 down to 2. Two bits, not 3. Oh, come on. And so now this, I'll leave it there for the moment, but I'll just delete this part. Okay. And then this, let's come up on top. All right. So now what we're trying to show is that whatever happens, so this one goes away too, by the way, while we're at it. It's only 2 bits wide. So now we figured out we got addresses 1 through 12. Now here's where the 1000 comes into play. We've only got 18 bits to work with, right? And so did I lose my 13? All right. I'm trying to decide if the buffer, yeah, we leave the buffer there. The write and the read, we'll leave the write and the reads there as a buffered. We'll do those up right in, hanging. I'm kind of doing it on the fly as we go here. Get rid of this little bit of green here, but all right. So write is going to go to write. Read is going to go to output enable. That makes sense. We're only going to need. We're going to need more than 2. Yeah, these 2 are going to select these guys here. But now what we're going to need here is we need to get to 1000 exactly and precisely, right? So let me do a little bit of quick paper math here. So we got 1000 hex, 00, come on, 10000 hex. So that's 16 address bits. And we were going to burn off 13 of those because 0 is going to be selecting between the top and the bottom. And we'll get fancy with that in a second. All right. So I've got 12 address bits there. I'm going to take 13, so I need 1, 0, 0, 0. So that's going to be, let's see here, 12 gets us up to there, so it's going to be 13, 14, 15, 16. And I need some zeros in front of it, 17 and 18. 0, 0. 1, we have to add 18 address bits, so it's 7. So, okay.
Professor?
Yep. Mm-hmm.
Sorry to point this out, but now the chips are labeled A0 through A11, but they're 2K by 8 chips.
Yes.
2K is 2 to the 11th.
Right.
Shouldn't there be A0 through A10?
Oh, they should be. Okay, so they're labeled 2K. That's not correct. They should be labeled 4K because that's what they said we had for the assignment.
So they're 4K chips then?
Yep, that's what we have for the problem we're doing here. Or 4K chips.
Okay.
Yeah. So hang on a second. Let me put it in there. And yeah, the original ones were 2K chips. These are 4K chips.
I mean, the original I'm looking at says 32. The original is 32K chips, which is just inconsistent.
Yeah. Well, let me go back. I got to go back to the original example here. So the problem said that we're doing 4K by 8 chips, right? See that here? The original problem was to do 4K by 8 chips, memory chips. Class 18 slide 1, and using this as the picture for reference. That's, yeah, so I mean, this is what we're designing here. The example for class, we're working out the example for class from this one. So if you've got your PDF file, we're looking at class number, and I'm sorry, by the way, this should be 18 here. Looking at class 18, address space mapping, and we're looking at slide number 1, and we're trying to build this memory space here. Okay. All right. So that's our EEPROM that we're working with at the moment. We're doing our EEPROM. And by the way, that's going to be chip select and read only. So there are the 2 SRAMs or 2 banks of 64K using 16K by 8 chips. So we'll get to that one in a minute. I think here too. What do we got here? We got 620. I'm kind of zeroed in on the EEPROM and doing that as we go on the fly. So again, apologies. All right, so this is the EEPROM, and actually, to be honest with you, it's not going to be bidirectional if it's EEPROM. It's going to be read-only. But tell you what, let's change this assignment just so that we make it so I can get to something that's going to make sense here. So at this moment, I'm doing this one here. Doing 2 SRAMs. So let's do this. 4 banks. Of 8K using 4K by 8 chips. Okay, so that's what I'm actually doing here. So forget, I'm doing number 2 at the moment. Come on. All right. Hang on, I'll get apologies for taking so long on all this. Fill, no fill, line wants to be red, please. And it wants to be a lot heavier. All right. So this is the one I'm working on here right now is number 2. I've changed that. I'm doing an SRAM that's 4 banks of 8K by 4K. Okay. And it's going to be at this starting at address. Starting at address 1000. Yes, I'm sharing all four chunks, all 4 banks of RAM, all 5-star. Closer. Anyway, let's go back to this for the moment. All right, so each one of these is 4K by 8, and I don't know what the number is, but anyway, that's what it is. Okay, so we'll come back to address 0 in a minute. So now I need 1,000 hex, and we got 18 address bits to work with. So starting at address 1,000 hex, I'm going to burn off address bits 12 down to 1, which means I'm going to have 1 0 0 0 and then 0 and 0 0. See, is that right? So that's going to be 12. That's going to be 12. This is going to be 13, 14, and 15, 16, and 17. I only need 2 bits. There we go. That's where I'm off. Okay, now, so I've got address bit 17 is the highest one to work with. That's correct. That's why we wanted to keep it. Except that address bit 17 wants to be a 0. Okay, address bit 16 wants to be a 1. So maybe I do want my 3 back there. Address bit 15 wants to be a 0. So let's do this. 16 wants to be a 1. All right. So, okay, so address 17, 16, 15, 14, and 13 are all going to be fixed. So I got to pick up the others here. So let's put them back here. Bring you guys down. Put you down here. Because I got an 17, 16, 15, 13, 17, 16, 15, 14, and 13. So I don't want quite that far down. One less than that. Let the bottom one remain grounded. And so I need a 14 and a 13 somewhere. Grab these. So you guys at least getting an idea of kind of how I'm doing this on the fly. So drawing as well as making them work. All right. So I'm going to need 17, 16, 15, 14, and 13 to get my contiguous address range. Okay, so I stop at 12 going up this way. This is going to give me 13, 14, 15, 16, and 17. Now, to get 1,000 hex, 13, 14, 15, and 17 are all going to have to be zeros. How can I show you that quickly and easily? So let's do this. Here we go. Go down here. All right, so I've got 0, 1, 0, 0, 0, and 0. Okay, and by the time I get there, do one more, and this can be a smaller font, please. What size do I want this font to be? Where is it? How do I get a smaller font? Here we go. All right, that has to be half that. So this is 17. Let's make it an even different color. Here we go. All right, so I got 17, A17, A16. Machine's running not too slow, but he's doing his best. All right, try this again. All right. Yeah, he went back to full size, didn't he? All right. A17, A16, A15, A14, A13, A12, and offset, jigger these around a little bit. So here's 13. Here's 12. Here's 14. Here's 15. Here's 16. And here's 17. All right. So here's what I'm trying to do with it. And let's move these guys over a titch more. Is that helping a little bit? Not the split A. Okay, we'll put the split A back. All right, so one more notch out. Not too many, hopefully. Let's bring this up a little more so we can see it while we're talking about it. Get them where I want them to be. Okay, so that'll work. All right, so notice that to select which particular location we want in the particular memory, we figured out we needed A12 down to A1. We're going to get BHE and BLE in there in just a minute, I promise. So working our way down, we know we decided we needed A12 down to A1. Okay, that leaves a 13, 14, 15, 16, and 17 because we've got an 18-bit address bus to work with. So A12 I've just put in here kind of for a bookmark. A12 can change, so that should actually probably be an X rather than a not bad. Let's leave it like that. I'm doing it on the fly. So actually A12 I've already got used, so I don't necessarily want that to be there. All right, let's put it there. Come on, give me an address. A letter, please. Put an X there. All right, so address 12, we're using up above, right? But in terms of groups of 4, okay, the next 3 that I've got, I should show 12 more zeros here that become 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. There'll be 12 more zeros over here, but I'm only worried about the top zeros we're working with. So 13, 14, 15, 16, and 17 are what I need to push through this buffer here because these are going to kind of become some of my control bits. Okay? BHE signal is used. So what happens is ultimately BHE is going to go down here and BLE is going to go up here as one of your control signals, one of your valid signals. Okay? So let's do it this way. We're going to do BHE into here. BHE, and we'll do a smaller font. And it wants to be a different color. Let's use it green since that's what he's got there anyway. Okay. And he wants to go up here a bit. All right, so BHE goes there. And that's probably also going to come through my buffer, or I may need to add another extra buffer. Okay, so BHE and BLE may be coming through here. So I may need another one of these buffers here to make it work. But I'm going to push BHE up there, and I'm going to push BLE down here. BLE. And let's do one more thing here. One more time. Come on. Come on, computer. One more time. All right. So BHE is going to select, I got it exactly backwards, go figure. So there's BLE, here's BHE. I want to wipe out that. All right. So now, we got questions. BHE, they're going to actually, they're going to come through this buffer here, or I'm going to double this buffer up. I'm going to make 2 of these buffers, and one's going to only care, maybe the other buffer is going to have BHE, BLE coming into it. Okay. So let's try and show this here real quick then, maybe. We got room for that over here somewhere. So BHE and BLE are coming through here. Another one of these. I'm just going to cut off the top part. They got to get this somewhere else. Let's put that up. Will it fit up there? Yeah, well, okay. All right. So I got another buffer down here, and this has got BHE coming into it. And BLE is coming into it. Okay, so these wires are green here, and they're going to the respective places they need to go. All right, so now I think that's pretty much what I'm looking for most of this. The thing is, this is going to change here. I'm going to use, how am I going to select between the top and the bottom? I'm going to use A13 to choose between the top and the bottom. I no longer want 2, I only want just the wire. That going to be the way I want it to go? Let me think here. No, because I got to use 2 to choose. Hang on a minute. 1 through 12, I've got to choose between the 4 more at that point. So I guess I've got this wrong here. Sorry. I need 4. I got to do this wrong. I've got them wrong. Got them wrong. Confusing you guys. So I'm going to go back to, I'm going to need 2 bits. Those are going to be 13 and 14. Yes, 13 and 14 should do it for me, because I need the extra 2 bits. All right. So I got 2 more X's showing up here. All right. So A12 goes up here. All right. And then we'll do this. A13 and 14 here, these guys. All right. Those are going to choose now which one of these 4 goes low. And then, so A17 and 15 have to be 0, and A16 has to be a 1. And we got fancy, we weren't choosing back between, BHE and BLE are active lows though, aren't they? So how can we do this? How can we do this? So what I'm going to do is I'm going to, let's do it this way, because I got to do this on the fly and I'm running out of time and stuff. So I'm going to have an OR gate. I have an OR gate here. 2 lows gives it to that one. In fact, let's do it this one where make it red after all. All right, and I'm gonna make this. All right, so this is gonna be an OR gate. I'm just gonna label it that way. All right, and I'm going to take. Let's pick A15. Got to be a 0? Yeah, if it's not, we're going to be fine. All right, so I'm going to take A15, and I'm going to put it in one side of that OR gate, if I can get it to come down. A15 is going to go into one side of the OR gate, and BHE is going to go into the other side of this OR gate. I can get it to move without scrunching. One more try. BHE and A15 go into one side of the OR gate, and then the output of that goes to this guy here. All right. And the other one is going to get A17. Do A17 into the other one.
Professor?
Yep.
So this bit of memory, this is the SRAM. This is starting at what address?
So it's starting at address 1000. So let's see, I'm just going to draw a line.
And which page of the project for today says 1000?
This is our hypothetical example.
So this isn't one that was on the lecture for today.
This is the one that's on the lecture for today, I think. I'm trying to get there.
Because that one says 4000. I see the EEPROM starting address range. I don't see where it says
I changed that a little bit. So sorry. Okay, so here's what I'm doing. I've got a modified thing from what I handed out. So I'm doing number 2. I'm doing an SRAM that's 4 banks of 8K using 4K by 8 chips. And it's contiguously addressed starting at 1000. So I've got a different. I changed it from what I handed out to you guys. So take a picture of what I got up there now. And actually, this is the one I'm working on right here. Is this new change thing here, because I couldn't do it quite fast enough to. I'm not going to get all 4 of these. Not while I'm trying to do it on the fly with drawing it as I go.
Okay.
That's what I'm doing here. This one here.
Ours is a completely
yours says something
different one.
Yeah, yours is different. Yours is different. I changed number 2 to be SRAM, 4 banks of 8K. So it's the same thing as the EEPROM, except that's now SRAM. So I just made SRAM to be the one I'm going to use, because this is SRAM I'm working with, not EEPROM. EEPROM's the same thing, except that all you have to do is have a read instead of a read and a write. So I did change it, yes. Going back here. So A17 is going to go there. I'm going to break this connection here. No. And then this one's also going to be the same thing. I'm going to break this connection here. And I'm going to put a wire from here down to this same OR gate. Somewhere like that. And then I'm going to have a wire from this one down to A17, like that. And I'm going to have A16 now. I'm going to run to this. This goes, okay, except I can't do that. I don't want to do that. Hang on. All right, so that's going to work there. This one's going to be A17 for both of them. And I'm going to have another OR gate. And this is also going to have A15, but now it's going to have BLE going into it. I think I'm getting what I want to have here now. And so that then is going to be going, as long as we got that stuff there. That then. Oh, come on. You kept wanting to stretch it on me, and now all of a sudden you don't want to stretch it. There you go. Ha! The rest of this disappears. That has to stay there. All right. So now I think that's the way I want to do it. And A17's got to go all the way up to that guy. All right. And then finally, let's do it this way. A16. This wants to be green. A16's got to be the active high. And we put in a line. Again, sorry guys, I'm butchering it today, but all right. So A16 now wants to go to this. Let's do it down here. A good spot. And A16 also wants to go to this here. Okay, I think that's what I want for the whole schlemiel. BHE is coming through and being buffered. Okay, so what's going to happen now is because I've got this addressing, let's go back down here, this addressing decode going on. So A16 has to be a 1 to enable this guy and a 1 to enable this guy. A17 has to be a 0 to enable this guy and a 0 to enable this guy. And then I have to have BLE to be a 0, okay, to enable this one. That has to be a 0, and A15 has to be a 0 to enable this guy. BHE has to be 0, and A15 has to be 0 to enable this guy. Now, there's one other hand-waving thing I'm going to do here. I'm assuming that you're either going to have both BHE and BLE low, or if you're only going to want to access the bottom part, you're going to only have BLE be low. Okay? Your write enable and your read enable are going to split out. Write's going to do the write, read's going to do the output. So if you don't have the low and the bottom bank activated, then you won't be reading or writing to that bank. So I think that's the way I want to do the whole thing and have it done. And that's kind of designing it a little bit on the fly, but kind of, so you kind of want to think about what you're going to be decoding. And then the big thing is that we're going to use address bits 13 and 14 are going to be selecting between which one of the 4 elements in the bank we're going to be getting. That makes sense? 16L8 is what you need for your decode. If you want to use that, you can use that. 16L8. Oh, this is 74LS138. So either way, you can use a 16L8 for the decode, or in this case, we're using the standard 74LS138. Okay.
Sorry, this is a silly question. Why are we?
No problem.
So why is 1000 going to be A16? Because 1000 hex. Right. Doesn't that mean there's a 1s in the A13th place?
No, I think no. And I keep saying 1000 hex. I should say it's 1. It's 10,000. 10,000. I always think of it as 1000 hex, just because that's me talking off the top of my head. Apologies. So going back to the slide here. So 0x1 with 4 zeros after it. And if it's 18,
4 zeros. Okay.
4 zeros after it, not 3. Apologies for keep saying 1000. I kind of do that for myself mentally, and it's not all that clear. But so the bottom 3 sets of zeros, 3 hexadecimal zeros, are going to get you from A0 through A11. Okay, but we're going to use that bottom address bit 0 to choose between the top and the bottom. And it said in the slide up that previous example then that A0 equals BLE, active low. So I'm not sure if that's been entirely completely helpful. Hopefully I didn't lose everybody in that process. I will do 2 things, I promise. One is I will make a copy of this and I'll put it up on the, I'll send out an email to everybody. I'll make a copy of this and put it up on the class, as well as, here's what I'm going to do. I'm going to expand this a little bit more. Let's do one more thing on the fly here. Let's do this. Let's go back here. Sorry. We'll do this. And we'll do this. I can bring it into the world where it needs to be. Give me another one. And we'll do this. We keep confusion down at least a little bit. And this. All right. So now we come back here. And we go back up there. All right. Hopefully that'll make some sense. So this is the example that I did. I worked up here. Okay. Kind of on the fly. This explains what the addressing range should be and exactly the thing that I was working up here. Okay. I'm going to create these two little OR gates. A17 is going to tap off to those guys. BHE and A15, both of those have to be low. And A15 has to be a low to do this, the top 0 here for the bottom of that hex. That 0 there needs to go in. Okay, and then I'm assuming BHE and BLE are coming through this guy and then going off to where they need to go here after they go through another buffer. Okay, does that help a little bit? Hopefully. I mean, for those of you guys who already knew all this didn't do much, but for those of you who didn't, hopefully this is helping a little bit. So I'm going to put this picture up on Blackboard. I'll save this as a drawing, and I'm going to put that other thing that we talked about earlier on. Bring this back over here. I'll also put up the that a little bit small to see. Hang on, I got something covering here. I'll also then put up the Verilog demux code we put together. I'm not going to swear by this, but I think hopefully most of this will work pretty well for you guys. Okay, if somebody gets a chance to try the Verilog, it doesn't work, let me know and I'll try and fix it as quickly as I can. But that's kind of, you guys kind of at least got an idea of sort of my thinking process and kind of what I go through as I try and do this sort of stuff on the fly. Hopefully it's not completely bad. You know, what you do is you start looking for what you can do for your enables here. I'm going back to this a little bit more then. You start looking for what you can do for your enables and how you can take advantage of your enables. And do I need to add a little bit of extra logic like an AND or an OR gate? What values do I need and how do I get them to decode? And these two bits are going to be choosing between the A and B. And then actually I had that right the first time around. Address 12 is going to be used up in my 4K addressing range here. Are there any other questions on that? Why is 74 so much different on KiCad? That I don't know. 74 LS 138 is different. Okay, Cameron, how's it different? '74 LS 138. It may look different. It may look a little bit different in terms of the thing, but it should still have the same pins and everything else, the same functionality, I think.
The one on KiCad includes a power and ground.
Oh, okay. So yeah, you just tie the powered up to, looks different. Use the IEEE. E1, I think it looks closer to the one we use. Okay. Yeah, I don't have the IEEE one, sorry. Not handy. And we're about out of class time. We're already about 5 minutes over.
So how does this decode the 10000 hex address? I'm completely missing what it's doing.
It has to start. So what you're doing is, all right, come back up here. Now I can go down there. Just get this out of the way. So everybody else, except there's one other guy I need to talk to about your exam, but everybody else, you can head out unless you want to stick around and listen to all this. That's fine. sketch this in a little bit more. All right. So what happened is that I changed the scope of the problem a little bit here just so I could make the thing work. I realized I wanted to have an SRAM so I could have a bidirectional read and write. And so I made it to be this particular example here now, which it doesn't hurt to see a little bit of a different example anyway, I suppose. So we got 4 banks of 8K using 4K by 8 chips, okay? And there's an active low chip select read and an active low write signals.
I already lost that. We have 4 banks of 8K. I'm counting. We have 2 banks of. How do you get to 4 banks of 8K?
All right. So each pair of these is a bank.
Each pair is a bank.
Each pair is a bank in this example. So this chip and this chip makes 1 bank. This next 2 pair of chips make a second bank. The third 2 chips make a third bank, and the 4 2 chips make a fourth bank. That's the 4 banks. 4 banks of 8K. They're 4K by 8 chips. So so a bank is 16 bits wide, 16 data bits wide. But the individual chips only have 8 bits in each of them, right? In terms of data. Are you with me on that?
Can you repeat? I'm sorry. I'm not. Okay. The numbers
aren't adding up. All right. So the chip is only 8 data bits wide, right? The chip is only 8 data bits wide, 0 through 7.
Yes. So is 1 bank both a high and low? Is that the idea here?
So 1 bank is 16 bits wide. So yes. I use 8 data bits here and 8 data bits here. This has got the data range 0 through 7. Data bits 0 through 7. This handles data bits 8 through 15. So a bank is 2 chips. CS is activated when the top bits are MSBs and are appropriate for the bank. So the CS of the top bank is here. Did I have the switched around? You're right, I got them backwards. Sorry. No, I got them right. BLE is on the top, BHE is on the bottom. So data bits 0 through 7 are going to the top half of the bank, and data bits 8 through 15 are going to the bottom half of the bank. And then they're both selected together by 0 coming out of the 274 LS 138s. The next bank is when you're going to 1 here. And the third bank is when you're going to 2. And the fourth bank is when you're going to 3. So that's 4 banks. And what selects between the 2 banks are address bits 13 and 14. So address bits 1 through 12 choose where you are in the individual chip. Address bit 0, which is BLE and BHE, address bit 0 chooses whether or not you're picking a top half or a bottom half, assuming that BHE is active all the time. And then address bits 15, 16, and 17 have to be uniquely decoded to pick out where you are in the total address range, your 0. So your hexadecimal 1000 basically is going to be 0, 1 with 4 hexadecimal zeros after it. So it has to, these top 2 bits have to be 0, 1. This bit also has to be a 0 as well. And then the remaining 4 hexadecimal things, with the exception of A15, are going to go from 0 to whatever in terms of addressing. So you'll count up to A12. When you count all the way through A12, then A13 goes to a 1. You'll go from the bank 0 to the next bank 1 going on up here, these 4 banks.
So first off, we're turning on at when the 16 we are turning on at 10000 hex.
Yes.
And we are using
And when you
up
do that,
to pin 13, sorry, up to pin 14 for the indexing. So at what point are we doing the bit of logic that decides we only turn on at this higher range? Because
at 1,000?
Yeah. Well, at
So,
10,000. I'm not
or
following.
10,000, sorry. So what limits you to 10,000 is address bits 15, 16, and 17. 15 and 17 are in red, so 16 is in green. So if I go in here and I go A16, in green, that'll do.
And G2A, G2B, these are enables for these chips that are active low. And the two enables are ANDed
the
together.
bubble means it's an active low. The bubble, yeah, they're all ANDed together. They all have to be that particular value in order to work.
They all need to be zeros to turn the chip on.
No. G2A and G2B have to be zeros. G1 has to be a 1 in order to turn the chip on. So A16 has to be a 1 here and here. A17 has to be a 0, which gets you 2/3 of the way there now. That has to be a 0. And then both A15 and the bank select thing, which is an active low, has to be 0 to go into this, to turn on the bottom bubble. So you have to have all three of those active. For G1, it has to be an active high. For G2A and B, it has to be an active low. And that's why I chose A16, since A16 has got to be a 1. That's why I chose A16 to activate the active high. I chose A17 to activate one of the active lows. And then I need both A15 and the bank, the BLE and the BAHE, which are active lows. Both those have to be a low in order to turn on this bottom bubble. And C has to be held low in that case.
So we're turning on when pin 17 is low.
Yep.
When pin, with the cross to that, so
A16 is a 1.
That's supposed to be pin 16?
That's pin 16, yeah. A16 is going in here.
Okay, so that's A16.
That's A16.
When A16 is a 1,
yep.
When A15 is a 0.
Right. And you're selecting the bank.
Right. So BLE is a 0.
So when BLE is a 0 and A15 is a 0, you're going to be selecting this guy here. So when you've got your address that ends in 0, the lower part, that's where it's coming in here. This thing right here. When address 0 is BLE. Okay. And BHE is going to be active whenever you're running an access.
BHE turns on when? It's always on if we're trying to pull 16 bits?
That's right. It's always on when you're trying to pull 16 bits. BLE is only going to be on uniquely when BLE is going to be a 1 only if you've got an odd address. BHE is going to be on for both of them.
If we were just incrementing by units of 16 bits in our code, then we should be accessing memory always with the A0 off. Yes, no?
As long as you're going to be going for, in this case, it's a 16-bit addressing, then bit 0 is always going to be a 0 for any group of 16 bits. Now, I'm not 100% sure this is going to work with the BHE. I was doing a little hand waving there, but I'm pretty sure BHE is going to be active for any access.
And so
typically you're
what
going to enable
happened?
both banks. Typically you're
What
going to enable
happened?
both banks
Yeah, okay. So how is
to
this
get all
going to work
16
with
bits out.
the if the 8086 is doing something else other than accessing memory in this system, in this section? Either it's
So then,
accessing memory
so
elsewhere
if
or
you're
it's
going to
accessing.
be in the range, if you're going to be in the range, if you're going to be in the range from 0x1000 up to 0x, in this case for 4K, up to 0x 1000 and no. So you'll go from 0. So the address range for this, that's a good question, is going to be address range. Let's write that in. ADDR range. For this particular example, let's make it black text now rather than green. Address range is going to go from X. We got X. Does it? Yeah, 0x. 0x. Where did it go? 0x. Come on. My poor computer is confusing me and himself. Why is he dropping away when I move him somewhere? All right. Let's try that again. Sorry. Address range for this one. ADDR range. Yeah, I think that's right. Exactly right. It's going to go from, but I'm going to do it in hexadecimal. 0x 1, 2, 3, 4 to 0x 1, and I'm going to have 1. It's going to go 7. That's what's doing wrong. 1, 7, FFF. That's the address range for this particular design.
So let's
Does that
say
help, Matt?
yeah, but furthermore, let's
Is that
say
correct?
that the 886 is reading writing somewhere else. It's
Yes.
some other piece of memory somewhere, and BHE is flipping, BLE is flipping, and read and write are flipping. We have to make sure that this doesn't do nothing, right? And
you're exactly right.
How do we?
What's going to keep that from doing? What's going to keep that from happening? You're going to be in some other address that's going to be bigger than. So if you have an address, let's say A16 bit is 0, right? So if you're below 1,000, if you're below, or I'm sorry, 10,000. If you've got a number less than 10,000, say you're going to address 70, 0x0070x. Okay, all right. A16 is going to be a 0, right?
Yeah.
Okay, all right. And so if A16 is a 0, then this G1 is going to be a 0, so neither of these buffers are going to select the chip selects. So the write enables and the output enables to these memories are going to be popping around, but the chip select's not going to be happening to any of those memories. If you've got an address less than 1,000 or 10,000 hex. Okay. Now the other possibility is, what if I've got an address that is, say, maybe I've got 0x1800. 18 with 3 zeros after it, right? I'm just the next address past the top address in my range.
Yeah,
so
that's
I've
the
got
one I'm confused on.
0x180000. If that's the case, then A15 will be a 1. Both of these will be forced to 1, and G2B won't be working on either of these guys.
Okay, so it's particular how we set these OR gates up, because there's potentially a combination of OR gates here that wouldn't work.
Well, you could the only thing that would make those OR gates not work at this point would be if BHE wasn't active for both accesses. But 815 is going to protect you against any address greater than 0x17FFF. Okay. A15 and or A17, depending on how big the address gets. So any combination other than 010 for these 3 bits means you're not going to decode. And anything other than 010 is going to be some address range other than between the 2 sets of numbers we've got set up down here.
Okay. So then if that... All right, so I'm following that now.
Okay, good.
On a slightly different point, though. We're using the 138 328 decode chips, right?
Yep.
Is this what we can use in the project? Because if you've been, I mean, the chat's been talking about how we've all been trying to use 138s, but the TAs have said that we need to start using PLDs, even though the project description says to use 328s. Can you help clear up some confusion here?
So, I mean, first of all, number one, I'm definitely gonna stick with what they're telling you in terms of what chips you can use. You should be able to write up the code to make your own 130. You should be able to write up the code to make your own 138 if you need to, right? So if I was writing code for this particular situation here, okay, I've got an input A, B, and C, and G1, G2A, and G2B, and I want to write that up to look like a 138. I'm going to have 8 lines. So continuing down here, I'm going to have, let's see, let's get a new one. Let's get a fresh one because I don't want to mess this guy up.
I'm so sorry, but I mean, I can do that in Verilog if that's what we're doing. I'm just confused if that's what we're doing, because they said you could use it, and now they appear to be saying you're not. You're saying Verilog. They said VHDL. They said that was like Verilog. Are they one and the same? What are we using here?
Yeah, VHDL is not much different than Verilog. If they're saying you're supposed to use VHDL, then apologies for showing you the answer in Verilog, because I assume that was what people were looking for. Hang on, let's get you the same thing. Actually, it's not much different at all.
Okay, because that was what I was... I'm still confused of what the clue VHDL is. We've had no descriptions or prior knowledge.
All right.
I mean, the project doesn't mention VHDL. Well, it does say it if you use PLDs, but it was unclear if that meant that if we didn't use PLDs, we could not use it.
Okay. Case cell is when. All right. So let me do the same thing in VHDL. I do have somebody still hanging around that was supposed to talk to me about not getting your midterm grade back yet. Is that true? Are you still here? Can you say something? Okay, good. All right. Brad, let's do this. Give me your phone number. I'll call you. I'll let you go if you want to go. If you want to stick around, you can. But give me your phone number. I'll call you once I get through with Matt here. You can stay. Okay. All right. So stick around.
I can hold on. You can address him first if you want.
No, that's right. That's right. Let me get this going here. All right. So I'm not sure about the module stuff. In a little while, I'm a little rusty on either side. So we don't want a test bench. What I want is entity. Okay, so this is what the VHDL is going to look like here. I have something like library.
Yeah, for what it's worth, I just took a peek back. All the project description says is include your PLD code. It doesn't even specify a language.
Right.
Are we using VHDL there? Help.
That you got to talk to them about, I'm afraid. I'm going to have an entity, a module, and he's going to have a port. Parentheses, and we're going to have cell. Which is going to be a colon in, and he's going to be std logic. Needs to be vector. I'll let you guys see. Vector. Sorry. And he's going to be 2 down to 0. Close parents. And you got a semicolon. Yeah, that's right. And then we're going to have Z again, which is going to be colon out std logic. Oh, yeah, he's going to be a vector too. Vector be 7 down to 0. And I'll have my close parentheses there. And then I'm going to have a semicolon after that. And I'm going to end. Yeah. END demux 16L8. And I got a semicolon there. And I'm going to have, well, let's leave it there for the moment. Architecture. May get cut off here. 2 minutes. If I do, I'll keep going. I'll put this up separately. Behavioral.
If you just want to put that out later, that'll work just fine. I don't think it does much good to watch.
Just in case I get cut off, I'm going to keep working on it here. But if I get cut off, you guys will know. Is, and then we go begin. And we're going to create a process. Yeah. And it's going to be sensitive to cell. And then we're going to have a Z0. Except that now I got to have a Z0 is supposed to be going to be set to this. And he's just going to be quote one quote. Like that. And so now I take and repeat this guy. And this is going to be 2, 1. Sorry. This will be 2, 3, 4, 5, 6. And I'm going to need one more. 7. These guys. Gonna have a case, I think, on cell, except that now we have to have an is after that. And then we're going to say when double quote, and we're going to have a little bit different arrow thing here, equals that. He's going to get assigned a 0. And now, I think I got a semicolon after that, right? More. 1, this becomes 2, this becomes 3, this becomes 4, this becomes 5, and 4, 6, this becomes 7, and then we're going to say end case with a semicolon. And we're going to have to come back over here. I'm going to say end process, leave with a semicolon. I need a space there for the end case, end space case. And then we're going to have end behavioral. I get the semicolon. I think so. That's what it looks like for VHDL rather than Verilog. We got you still? Matt?
I'm still here.
Okay. So that's how you do it for VHDL as opposed to Verilog. I'll put both examples up. I'm 90% sure that's going to work. I mean, I'm not sure if I got a syntax error or a semicolon somewhere or whatever, but okay. I think that'll do it for you. You can see they look a lot alike, right?
Just to point out, I mean, the TAs haven't given us any briefing on what is VHDL, how to use VHDL, how to set up VHDL, if it's on GL. So that was a great piece of code.
Right. So do me a favor. When you go to the class, okay, when you go to when you go to your discussion, your lab discussion on Friday,
yeah,
tell them that you have had training in Verilog, but you haven't had training in VHDL.
Yeah.
Okay.
All right.
We don't want you to be learning new stuff.
Just point out, because you are giving this out, but I have no clue how I would even attempt to execute this.
Yeah, well, I mean, it's not too hard. You look at the similarities between the two languages and you look for one slightly different. You know, to be honest with you, Matt, I never had a class in either language.
Yeah.
I do this by going online and looking up, doing a Google search for something closest to what I'm looking for, and then I adapt it to the particular thing that I need. So, yeah. I mean, that's the, I appreciate not having had a class. I mean, I've never had a class even in an 8086 or an 8086. But the only class I ever had was in a 4004, and that was just, here's the chip, here's the data manual, go have fun.
Oh no, I realize that we can figure these out on our own. That's not the point. The point is, right. We're supposed to turn in a program for a chip in a hardware design language. Right. But we're supposed to model this entire circuit in VHDL. We're turning in just this one file. Do we need this file in another startup? I mean, if there is an explanation from this class, how do I know I'm conforming to your format? It's not one of these things where like, I know it was right because it worked, because we're just going to turn it in. We're not going to know.
Well, I mean, there should be some way to verify the language, I think, anyway. But
if there is, I would love to know about that.
There is, and there's Geeks for Geeks, I think will at least tell you if it compiles or not. You might try that.
I meant if like there was a test script available for the project that. I realize there's stuff on the internet. That's not what I meant.
Yeah, Geeks for Geeks will tell you if your syntax is right at least, and if that kind of sort of stuff, I believe. So anyway, and they'll even tell you how to write a test bench and test it out if you want. I mean, I'm the website that I got most of this from, that I kind of adapted to be 8 rather than 4, because they had a 1 to 4 demux. I needed a 1 to 8 demux. They have a little test bench that you can run a simulation on and test it out and see if you got the right code. All right, I gotta let you guys go.
All right.
But I do want to talk to Brad. So Brad, stick around. See you tomorrow, everybody.